In this module, we'll solve the Schrödinger equation for an electron in a central potential, which is also known as the hydrogen atom problem. And we're going to do this in a series of steps of increasing complexity with the goal of seeing explicitly where the quantum numbers that we're familiar with in the case of a hydrogen atom actually come from. So that in the first step, we'll solve the Schrödinger equation for a particle that's confined to a ring in space, but which doesn't experience any external potential. So it's a free electron, but confined to move only on a ring. Then we'll add an additional dimension and solve the Schrödinger equation for a particle on a sphere. So again, the particle is a free particle. It doesn't experience any potential, but this time it's confined to be anywhere located on a sphere with a constant radius. And then the last step, which is the full solution of the hydrogen atom problem, is a particle in a Coulombic potential. So now the particle is not constrained to be at a fixed radius. It can distribute itself towards the center or away from the center of the sphere in order to find the minimum energy solution. Okay, so let's start then with the particle on a ring. So our problem looks like this. We'll confine our electron in the xy plane to be sitting somewhere on this ring, which has radius r. And our task is to solve the Schrödinger equation with v is equal to 0. And our boundary conditions are such that they constrain the particle to the ring of radius r. And this problem is much simpler if we use polar coordinates. That x is equal to r cosine phi, where r is the radius, and phi is this angle here, and y is equal to r sine phi. So our Laplacian del squared, which appears in the Schrödinger equation, is d2 by dr squared plus 1 over r d by dr plus 1 over r squared d2 by d phi squared. And because r is a constant, our particle is constrained to be at a constant r, this reduces to del squared psi equal 1 over r squared d2 psi by d phi squared. And again, this is because psi is a function of the angle of phi, but it's not a function of r. So we can write down our Schrödinger equation is minus h bar squared over 2m r squared d2 psi by d phi squared is equal to E times psi. And the boundary conditions are that the wave function at angle phi plus 2 pi must be equal to the wave function at angle phi in order for the wave function to not cancel out. Okay, so this is the problem that we have to solve subject to these boundary conditions. This is a rather simple differential equation, and we can solve it by inspection. And so we'll take as a trial wave function psi equal to some constant for normalization times e to the I times some number m sub l, which was going to become our quantum number, times phi. And we'll substitute this into the left-hand side of the Schrödinger equation, which is minus h bar squared over 2m r squared d2 psi by d phi squared, which, taking the second derivatives, gives us h bar squared over 2m r squared times m sub l squared times psi, which is a constant times psi. So our wave function, our proposed trial wave function, is a solution of the Schrödinger equation. So psi is equal to a e to the I m sub l phi is a solution of the Schrödinger equation with energy E equal to h bar squared m sub l squared over 2m r squared. We can find the constant A by applying the normalization condition that the integral from phi is equal to 0 to phi is equal to 2 pi times the square modulus of psi squared over all phi is equal to 1. And substituting for the square modulus of psi, that's the integral from 0 to 2 pi of a squared. Remember, when we take the square modulus, that's e to the minus I m sub l phi times e to the I m sub l phi integrated over all phi, and we set this equal to 1. And this, of course, is equal to 1. So we obtain a squared times 2 pi is equal to 1, or a is equal to 1 over the square root of 2 pi. We'd also like to know what our m sub l values are. Because our m sub l quantum number, we already showed, determines what the energy of the wave function is. And for that, we'll apply the boundary conditions that e to the I m sub l times phi is equal to e to the I m sub l times phi plus 2 pi, which, of course, the exponent of the sum is the product of the exponents e to the I m sub l phi times e to the I m sub l 2 pi, which tells us that e to the I m sub l 2 pi has to be equal to 1. And in order for e to the I m sub l 2 pi to be equal to 1, m sub l has to be equal to an integer, 0, plus or minus 1, plus or minus 2, etc. There's one more property I'd like us to look at before we leave this simple problem of a particle in a ring, which is the angular momentum. And in this particular case, since the particle is confined to the xy plane, the angular momentum is equal to the z component of the angular momentum. And there's a number of ways that we can do this. Maybe the simplest is to write down that the kinetic energy is equal to the square of the angular momentum over 2mr squared, just from our knowledge of classical mechanics. And so then we can immediately write down that the angular momentum is h bar times m sub l. So the m sub l quantum number gives us not only the energy, but also the angular momentum of the wave function. The m sub l quantum number, which we just showed, has to have an integer value. So this tells us then that the angular momentum, the z component of the angular momentum, is also quantized. It can only take on certain well-defined values. So this is our first approach to finding the angular momentum. The second approach is to write down the angular momentum operator and the way that we do this is write the form of the angular momentum operator in terms of the position and linear momentum operators, and then substitute the form of the position and linear momentum operators that we know from quantum mechanics. So the operator for x is just multiplied by x. The operator for py is h bar over I d by dy. The operator for y is multiplied by y, and the operator for px is h bar over I d by dx, which in spherical polar coordinates is minus I h bar d by d phi. And once we have the angular momentum operator, then we can calculate the expectation value of the angular momentum by integrating psi star times the angular momentum operator times psi over all space. If we do that, I'm not going to work that out. You can try that yourselves. We obtain m sub l times h bar. The third way that we can find the value of the angular momentum is to see if the wave functions are eigenfunctions of the angular momentum operator. And if they are, then their eigenvalues are the values of the angular momentum. So let's work out the effect of operating on psi with the angular momentum operator. Obtain 1 over root 2 pi times minus I h bar d by d phi, acting on e to the I m sub l phi, which is m sub l times h bar times 1 over root 2 pi e to the I m sub l phi, which is m sub l h bar times psi. So they are and they have eigenvalue m sub L h bar. So again, the m sub L quantum number tells us the z component of the angular momentum, and because the wave function is an eigenfunction of the L sub z operator, this means that every measurement we make of the z component of the angular momentum will always give us the same answer, and that answer will be m sub L h bar. Okay, so a lot of physics already just in this very simple problem of the particle in a ring, which we'll now take to one level higher of complexity by looking at the particle on a sphere. And again, we're going to use spherical polar coordinates. So again, we're going to use polar coordinates. This time we have to use spherical polar coordinates, in which we define x to be r sine theta cos phi, y is r sine theta sine phi, and then we have a third dimension, z is equal to r cosine theta. And let me try to draw this for you. Here's the z-axis. The y-axis and the x-axis. And here's the ring in the xy plane that we just worked out. And the third dimension. So we have a sphere. And the angle phi is the angle in the xy plane, starting from the x-axis. The angle z, the angle theta, sorry, is the angle away from the z-axis, away from the vertical, starting from the z-axis, and the distance r is the radius of the sphere. Okay, in spherical polar coordinates, let me write out the Laplacian for you and try not to make any mistakes. So del squared acting on psi is now 1 over r d2 by dr squared times r psi plus 1 over r squared, all multiplied by 1 over sine theta d by d theta sine theta d psi by d theta plus 1 over sine squared theta d2 psi by d phi squared. This is very nasty, but since r is fixed, the wave function is a function only of theta and phi, and so we can get rid of any terms that have a derivative with respect to r. And so our Schrödinger equation is minus h bar squared over 2m r squared 1 over sine theta, d by d theta, sine theta, d psi by d theta, plus 1 over sine squared theta, d2 psi by d phi squared, equal to E times psi. This is very horrible, but we're in luck because this is a known equation. We call it a special equation with known solutions. So our approach to solving this equation will be to look them up. And the solutions are the spherical harmonics, which are described by two quantum numbers. They're always called capital Y, and they depend on two quantum numbers. The M sub L quantum number that we introduced already. Let me draw that so it's, we'll write that so it's clear, it's a subscript L. And they're functions of two variables, theta and phi. And the limits, the boundary conditions that the wave function has to repeat itself when it gets back to the same point on the sphere, give us restrictions on the values of these quantum numbers, that n can be 0 or any, L can be 0 or any positive integer, and that M sub L can run from plus L through to minus L in integer steps. And so one can look up the values or the expressions for these spherical harmonics. So an example, and we'll have a look at in just a moment at how they look like. The spherical harmonic with L is equal to 0 and M sub L equal to 0 is a constant equal to 1 over 2 root pi. The spherical harmonic with L is equal to 1 and M sub L is equal to 0 is a half root 3 over pi cosine theta. And we won't write them all out. One can, as I said, look these up. Let's take a look at what these actually look like. So these are visual representations of the first few spherical harmonics. And this is taken from Wikipedia. And the notation is such that blue is positive and yellow is negative. And they're shown in order of increasing L values. So this is L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3. There's a subtlety here, and these are visual representations of what are called the real spherical harmonics. So they're actually linear combinations of the actual spherical harmonics described by L and M sub L in order to obtain real parts. And the distance of the surface from the origin is giving the absolute value, again with blue being positive, yellow being negative, of the spherical harmonic in the angular direction, theta phi. And I think these blob pictures will be very familiar to you all as the usual form of the S and P and D and F orbitals. So the completely spherical, L is equal to 0 spherical harmonic is exactly the form of the S orbital. The L is equal to 1 spherical harmonics we're familiar with as the P orbitals. The L is equal to 2 as the D, and the L is equal to 3 as the F orbitals. More points before we leave the particle on a sphere. We could work out, just as we did for the particle on a ring, the energy, the z component of the angular momentum, the angular momentum. You can try these. They're of course a little bit more complicated because there's more variables. The math is a little more difficult. But following exactly the same procedure, we obtain that the energy is given by L plus 1 times h bar squared over 2 mr squared. M here is the mass, not the m sub L quantum numbers. The z component of the angular momentum, L sub z, is m sub L h bar, just as in the particle in a ring case. We still have, the particle is still able to circulate and is able to occupy the xy plane, so it has the same z component of the angular momentum. Now, of course, the z component of the angular momentum is not equal to the total angular momentum. The total angular momentum, which is the square root of Lx squared plus Ly squared plus Lz squared, is equal to the square root of L plus 1 times h bar. And this you could extract easily by setting the kinetic energy equal to L squared over 2mr squared. And again, the wave function, that's the solution to the Schrödinger equation, is an eigenfunction of the L sub z quantum number, of the L sub z operator, sorry, and of the operator for total angular momentum. And it's conventional to talk about it being an eigenfunction of the square of the total angular momentum operator, with eigenvalues m sub L h bar, as we already wrote down, and L plus 1 h bar squared. Okay, so that's the particle in the sphere. And now we're ready to move on to the full hydrogen atom problem, which is the particle in a Coulombic, which is just a 1 over r potential. And so now we no longer have a free particle, a free electron. Now the electron experiences a potential, which in the general case is given by minus z times e squared over 4 pi epsilon 0 times r. Z here is the atomic number, so in the case of the actual hydrogen atom, this would be equal to 1. In the general case, we'll keep the Z there to the general case. And so now our Schrödinger equation is has not only a kinetic energy term, but also a potential energy term. So it's minus h bar squared over 2m del squared of psi, where our wave function now is a function of r and theta and phi. Our particle is no longer confined to be on the surface of a sphere. It's also can vary in position, in radius. And the potential is minus z e squared over 4 pi epsilon 0 r psi r theta and phi is equal to e psi r theta phi. And now to solve this equation, we have to plug in the full Laplacian from the previous discussion without being able to make the simplification that there's no variation in r. So we also have to keep the d by dr terms. Again, we get lucky that this is an equation that people have solved many years ago, and the solutions are written down. And so our approach to solving this equation will be to look up the solutions. And the solution is that the wave function is now described by 3 quantum numbers, n, l, and m sub l. The l and m sub l that we had before, and now another one, n. And it's a product of 2 terms. One is the spherical harmonics that we obtained from the particle on a sphere problem. And the second are functions that depend only on r and are described by the quantum number n and l. So the spherical harmonics give us the angular component of the wave function, the theta and phi dependence, and they're described by the L and M sub L quantum numbers. This additional function r gives us the radial dependence. So we're very fortunate for this particular form, the 1 over r form of the potential. The wave function separates into a part which is the radial part and a part which is the angular part, which makes our lives a little easier. And the quantum numbers, in the boundary conditions, the wave function has to come back on itself when it gets to the same point around a sphere, give us that the n quantum number must be a positive integer. The L quantum number runs from 0 to n minus 1 in integers. And the M sub L quantum number, again, runs from L to minus L in integers. So these, again, this y functions, these are the spherical harmonics, which we can go and look up. And these r functions, we can also go look up. They're related to what are called the associated Laguerre functions. So just for interest, I made a list of these associated Laguerre functions. So let's look maybe at the first one, which has n is equal to 1 and L is equal to 0. And here the quantity rho sub n is equal to 2 times z times r over a0 times n, and a0 is the Bohr radius of the hydrogen atom. And our first radial function here we see is exponentially decaying from the center. As a function of r. And so it has the familiar form of the radial dependence of the hydrogen 1s orbital. Again, we could, in principle, if we had a lot of time to do mathematics, or we were good with MATLAB or Mathematica, we can work out the values of the energy and the angular momentum and the z component of the angular momentum. And what we'll find is that the n quantum number gives us the energy in this case. And the energy depends inversely on the square of the n quantum number with a whole bunch of constants, z squared m e to the 4 over 32 pi squared epsilon 0 squared h bar squared. Again, the L quantum number gives us the total angular momentum, which has the same form as in the particle in the sphere case. And the m sub L quantum number gives us the z component of the angular momentum. Lz is equal to m sub L times h bar. And again, the wave functions are eigenfunctions of the energy, the L squared, and the Lz operators. Okay, so then the case for the hydrogen atom that we've solved, if we just make an energy level diagram now, in terms of increasing energy, our lowest energy solution has n is equal to 1, and the only possibility when n is equal to 1 is that L is equal to 0, and when L is equal to 0, we can only have m sub L is equal to 0, so we have a single energy level, and this is, of course, our 1s atomic orbital. Next higher in energy are the energy levels with n is equal to 2, and here we have two options. L is equal to 0, which gives us the 2s atomic orbital, or L is equal to 1, and when L is equal to 1, we have three possibilities for m sub L, 0, plus 1, or minus 1, and these are our 2p atomic orbitals, of which there are 3. Let's go one more to n is equal to 3. Here L can be equal to 0, which is our 3s atomic orbital, can be equal to 1, which are our 3p atomic orbitals, of which there are 3, or L can be equal to 2, and when L is equal to 2, m sub L can be 2, 1, 0, minus 1, or minus 2, and these are our 5 3D orbitals. So that's the end of the solution of the Schrödinger equation for the hydrogen atom, and thanks for listening.